this up in full screen mode. All right,
Okay.
there we go.
Well, thanks you guys so much for coming. Really appreciate it. And I just wanted to introduce us real quick. So this is our Seattle Continuous Delivery meetup group, and Dev9 is the one that puts it on, and so thus we're speaking tonight. So event streams in the cloud, this should be a really great topic. And I just wanted to give you just a brief overview of Dev9, just my little elevator speech. So Dev9 is a local consulting firm, and we focus on custom software development through the use of continuous delivery. And we mainly, our projects are centered around web services and web applications. So if you guys are interested in finding out more, we're happy to chat about that afterwards as well. So, and your two speakers tonight are Jeff Ramsdale and Chris Philipson. So I will let Jeff take it away.
Thank you. And again, thank you for coming this evening. Chris and I have, until very recently, worked on a project together for a large local travel business. And Chris has now moved on to another project, but we would like to talk about what we've built over the last year and a half, some of the problems that we were dealing with, the challenges we ran into, and solutions we came up with. And then we'll have some discussion time and take any questions you guys have. If you have short questions along the way, feel free to ask them. If they turn into longer ones, we'll just punt to the end and handle them in the Q&A. So the problem we were trying to solve is we had a business that had a legacy application that had a lot of log events. So when data would change, specifically lodging data having to do with hotels, database would typically store the most recent value for any given field. So what is the price for a particular hotel room for a particular day or a week or whatever. And when the value changes, they needed to be able to find out, well, what was the value in the past if they need to do any reconciliation. If they sell at a particular price, for instance, and then somebody says, well, it said it was supposed to be such and such another price, and I was billed the wrong thing. Or I was told that I was going to get free Wi-Fi, and then when I got there, they said that there wasn't free Wi-Fi. So they need to be able to have a history of what was available at a particular point in time in history. So they have a lot of historical data, not just the current value for any given field. So these are log events. They needed to store many millions of these. And so they already had a database in existence, but it was a very large clustered MySQL SQL Server database that was quite expensive. And they wanted a better solution. So we were brought in to look at initially a NoSQL option, something in the cloud, and something that would be more scalable, faster, and cheaper. The data would be streaming data. That is, there would be constant changes. Sometimes there would be batch loads of new data from a computer system that was doing wholesale changes all at once, but there would be many other changes that would just be coming in at a constant rate. We were also oriented towards breaking apart some monolithic existing applications, and we were trying to loosen the tight coupling from the previous iteration of the applications. So as far as how we were going about solving the problem architecturally, it's a write-heavy workload. They don't need to go back and do these reconciliations very often. Not that this is the only purpose for this platform, this data platform, but it's one of them. It's primarily write-heavy. And we needed to split the duty between emitting these events as events and then also doing the persistence so that they could be queried later and retrieved. We wanted to make sure that people were publishing well-formed data, not that they could just publish anything that they wanted to, so the system needed to be self-protective. So we needed to verify that the data was valid. We didn't want to persist duplicates, so we needed to do duplicate detection. And then if something in the system failed, we needed to be able to recover from that, understandably. And then we needed to be able to get their existing data, which was on the order of around 12 terabytes, I would say, migrated into our data system. Originally, we were oriented towards DynamoDB. As I mentioned, we were imagining that this would be a NoSQL problem primarily because it's unjoined data, it's unlinked data. These were just individual log lines, and it seemed to fit the use case. Chris will go into some detail on why we moved away from it and what we chose instead. But we also looked into the RDS options. Let me clarify. I guess I implied but didn't specify that we were pointed at AWS from the very beginning. So we were not evaluating other cloud options. We came in expecting to use AWS, and we ended up using AWS. There's a spoiler alert. There are other options that could do what we wanted to do. I think we're very satisfied with what we chose. There have been conversations along the way about how much do you want to be tied to a particular system versus able to move from one cloud to another. That's not really something we're going to concentrate on in this presentation, but it is a consideration, and if you guys want to talk about it more, we can talk about that later on. We didn't look at Redshift as a storage option, but it is something that we've evaluated a little bit later for some of our other data processing needs. So we can talk about that if we need to. And then S3 is used at various points in our system for some things. It's not a primary data store, but it is in use. As far as message queue providers, Kinesis probably should be at the end of the list. It's a more recent technology. I think it was announced a month after we started on the project, and we wouldn't have picked it up. I think at that point it was too raw. We did initially use Kestrel as well. It's not in use now, but that's also a queue provider that we used. It was a dying technology at that point. It had been basically abandoned. So Kafka and Redis are in use, and we'll talk a little bit about that. As far as processing the data stream, we use Apache Storm. There are other platforms that are out there. We never really evaluated them because this was the one that was already in use commonly, and so we maybe could have made a pitch for another tool, but we didn't have probably a strong enough pitch not to use the one that was commonly in use. So we would consider alternatives now if we could.
I saw Kinesis specification dated as 2013, so that means that you started your project at 2012?
No, I thought Kinesis was announced at reInvent 2014. Was that not the case?
I can confuse the numbers, but what I saw like on the probably confusing, like 2014, 2013, it's like close.
Yeah, no, we started in September 2014, so I think we missed when it was announced, but I think we would not have taken it on at that point. But we can talk about it later on as where it might fit in our architecture, or where it might for your use case if you wanted to do something similar. The pattern that we were implementing here, I've seen references to Lambda architectures and event sourcing. And there's some overlap on those, and our architecture has some resemblance to those, and we can compare those a little. But it's a pretty common pattern that you'll run into here that we'll be looking at. As far as our implementation, we use Java 8, Spring Boot, Spring Data, and Spring Integration. I'm sure if you've used Spring at all, it's a massive ecosystem. There's a ton of projects there, and we brought in little bits and pieces here and there as they provided utility to us. But we were pretty sold on the Spring ecosystem, and we're fans of that. But because it is so large, you have to be kind of choosy about which pieces you bring in and how much you take on all at once. So here's our essential architecture from a logical perspective. We have data publishers that are publishing events into our event engine, and those events are stored in the database. Not all of the types are actually stored. We emit some just as events, because not all of them need to be queried later on. So we didn't bother implementing the persistence components if they weren't necessary. Any of the querying would come from a read client, so that's reading the data that's stored in the database. The event engine would also emit messages to both Kafka and to Redis. Who has familiarity with Kafka? No, okay, not so much. How about Redis? Okay, so a lot of people think of Redis as a key value store, and it certainly functions very well as a key value store. The feature that we were really interested in was as a pub sub framework. So you can have n number of listening applications that subscribe to topics, and including wildcards, which is a pretty neat little feature. And then you can have event publishers that publish messages into Redis, and then all of the subscribers that match up their subscriptions with the topic that it was published to will be notified. It's very handy, super easy to integrate with, easy to test. There's a Redis CLI, so it's easy to just kind of hook up and subscribe and see the messages flowing through. We love working with Redis. The problem is that it's not reliable, because imagine that all of those topics are like zero-length queues. So if a message comes in, if there's not anyone listening at the moment that the message arrives, then you can't come back later and pick it up. You'll never get it. There's no mailbox. There's no queue. It's a zero-length queue, so you have to be there. For users who need to have, or clients that need to have reliable message delivery, Kafka is a better solution. And Kafka is a journaling system developed at LinkedIn, I believe, right? And it's capable of supporting super high throughput, millions of messages a second, and a lot of simultaneous consumers of the data. And because it writes everything into this journal on the disk, and then the consumers basically say, I want to go to this queue and read from this offset, and just start scooping the messages out, it can hand off messages very quickly. It's essentially pretty simple in writing these messages and then streaming them off. You have to do a lot of coordination around where you get those messages from, and make sure that you're not overlapping with another application that's like another instance of your application. That's what they call a consumer group. If you have multiple instances of your app that are all trying to read from the same queue, you need to make sure you're not reading the same messages. So there's coordination that has to happen. So historically, at least, Kafka has used Zookeeper for that. I think the new version of Kafka is able to store that information internally and simplify some of the interactions, but it's a little harder to interact with. So for ease of access, Redis is great. If you have to get the messages, then you need a solution that's a little more complex that's going to allow you to do that, and that's what Kafka is able to provide.
To try to use as many AWS services as possible, why not use SNS?
So that's a good question. SNS, in my understanding, I've used it relatively lightly. SNS is actually quite analogous to the Redis PubSub solution. I don't think that SNS keeps messages around. It's a subscription thing. You're either there or you're not. Now, you're maybe more liable to be there in an SNS scenario if you're using some hosted feature of AWS. So for instance, if you have a Lambda listening to SNS, you're liable to get that message because the whole system is designed that you always would have a Lambda there. But if you're talking about a service that might come and go on an EC2 instance, you're doing an upgrade of an app, and you want to drop for a little while and then come back and collect the messages that were posted while you were down, then SNS I don't think is going to solve that problem for you. Looks like Chris wants to say something.
I wanted to just say that if you're familiar with the AWS ecosystem, there's Elasticache, and there are two provider implementations of which Redis is one, and we definitely made use of Elasticache.
Right.
For Redis, the Redis provider.
Right. So just to clarify that, this Redis instance is the hosted AWS Elasticache Redis service. So from a client perspective, it's Redis. From a deployment and management perspective, it's an AWS managed service. And Kinesis, that we mentioned earlier, a couple screens earlier, Kinesis is, I think, probably architecturally quite similar to Kafka and serves a very similar purpose. So you could just as well use Kinesis in this scenario. There's also SQS, which I've been asked about before. But my understanding with SQS is it's not as suited to having multiple clients of the same queue, where with Kafka you can have multiple consumer groups, so multiple applications reading from the same queues, and they won't interfere with each other. I think SQS is really meant to be more of a one-to-one, like it would work in a master worker scenario where you're producing work and then you have a cluster of workers that are listening to that SQS queue. I don't know that you could have multiple different sets of consumers of that queue.
There's no fan out.
Right, no fan out. The last thing I want to mention here for my part of this presentation is that we had these listeners. So I'll start at the bottom. The original architecture, actually I'll start here. The original architecture was basically a CRUD app. You have a monolithic app with a database. You store stuff in it, you get stuff out, that's great. But if you have another application that needs to know about that change, it's not very easy to find out that something has happened. You can go and you can query the database, but how tight a loop do you want to do that on? Or you can set up some sort of a trigger on the database, but then that's an overhead that you really probably don't want to have to manage. And you would have to add maybe a new trigger for each of your apps, which means you have this sort of central maintenance cost. So really what you're trying to do is decouple your message producers from your message consumers. So as a side effect of pulling out this data source and making it scalable and faster because of the technology choice, which again Chris will get into, you're also basically putting a little point cut in there that allows the events to now be emitted, and apps can respond to those, and you can open up a whole new categories of behavior that were unavailable to you before. So that's what we're talking about here, where new applications can be developed to respond to the business events, and we're decoupling the producers from the consumers, and that has already proven to be quite valuable, and has led to, I think, to probably even more success for us as an application than just making a faster, cheaper database. Hand it over to Chris.
So this table here kind of spoils it because it's revealed all at once. But what you should take away from just a simple glance is, well, we chose Aurora. We looked at Dynamo, we looked at MySQL, and Aurora was kind of one of those timing things, because right around the time that we were kind of fighting some issues with scaling, mainly on the storage front for MySQL. As you can see here, the maximum storage is 6 terabytes per instance. We knew we had more data than would fit in a single instance. Yeah, we could have multiple instances, but we didn't want to take on that overhead. As Jeff mentioned earlier, we're working with log events, and there were something like 30 plus log events that we were responsible for, of which like the top 3 comprised 90% of the record volume. And I'll get into a little bit later about how we dealt with stuff like that. But some of the other pieces were cost as well. When you're looking at provisioning instances of databases, you have to look at what the cost is going to be there. And we looked at DynamoDB. We gave it an honest try. But for the kind of write-heavy workload that we were looking at, and for the bounded nature of, we knew we weren't going to grow beyond 12 terabytes anytime soon, and they were looking at wanting to maintain about 2 years worth of data, like a retention of 2 years. That would only scale up on present volume to no more than 1.5 times the current size. So we knew we were well within the boundaries. So to have them spend a lot of money, you get a lot of scale here. This is unbounded. This can grow to any size. But we didn't feel that was the right fit for what we were. Yes?
One thing I neglected to mention is our volume. We're talking about 100 million to 1 billion events a day.
Mm-hmm.
Yeah, just to give you an idea. Right. And then I don't know if they would necessarily know what Amazon Aurora is.
Right, I was going to get to that,
okay.
Absolutely. So Aurora is kind of Amazon Engineering's attempt at placing MySQL on steroids. There's all kinds of capability that they give Aurora, both from the fact that when you write anything to it, it's basically replicated across 6 times across 3 availability zones, so you get lots of redundancy there with your data. And the difference between a MySQL instance in scale as you're increasing write volume, with a MySQL instance, your levers are these things they call individual operations, and you can provision them on a per second level, and you have basically a ceiling with MySQL. There, you don't have that ceiling with Aurora. It just keeps on going and going and going, and it's done for you automatically. There's an additional cost to doing that when you provision MySQL, depending on how many IOPS you provision. It's going to cost you extra. What else can I say? Anything else I'm missing here? Yeah, so the highlights, basically.
The mention that it's MySQL compatible in terms of the driver.
Right. So you can use MySQL, the MySQL driver, or you can use the MariaDB client. And the MariaDB client is actually a better option for you with Aurora because it has some configuration that and tuning that's specially made for Aurora. So like if you're familiar with JDBC URLs, when you declare your JDBC URL for the client, you can actually specify like a master and a replica, a read replica. And we'll get into what that is. You guys familiar with read replicas and what they do for you? So if you have a database and you're write heavy, and at the same time you want to be able to make queries, and some of those queries might be expensive. Sometimes you can contend for resources, and you can get locks in the table. So if you have a read replica, what's happening is that as you're writing, it's making a copy and shipping it over to the read, and you can make connections to that read replica to do your querying. Meanwhile, you could be pumping new data through. Yeah. So this is what the physical architecture looks like. Kind of a deployment footprint is that we have this ingestion validation collection of EC2 instances. So a user, a system makes a post request for a log event. They can either post a single log event or they can post a batch of log events. And the ingestion engine will take that, and the first thing that it does is go, okay, you gave me something. Let me see if I know how to process it. So we have a manifest there that says, here are the types that I support. And if that doesn't, if there's no match, well, we then reject that. For batches, we're a little more friendly. We'll actually iterate through and let the ones that are good pass through, and the ones that are bad we'll report on those. So everything is good. It makes its way. We actually post to basically a facade. It's basically kind of an HTTP client to Kafka. It takes and configures a message suitable for publishing to Kafka. So we place that in the Kafka queue. And then we have, in Storm, we have basically, if you're familiar with Storm and its operation. So Storm is basically, you have spouts, which are things that receive work or items to be worked on. And then you have bolts, which are, you can think of them as processors. And so a spout will consume messages off of the Kafka queue and pass them on to these bolts to do something. So we have multiple bolts. We have a bolt that's responsible for writing back. So yeah, that's something I should mention. All the messages that are published to the queue are to Kafka are coming in on a private queue. So all 30 plus log event types are going on a single queue here. And then we're subscribing, we're picking them up, and then this bolt here says, oh, you gave me a type A. I will write back to this facade, but on a public queue, so that I can subscribe. And I don't know if I've got a picture here. Yeah, we do. Subscribers to the public queue. The next bolt will actually, for the streaming option that Jeff talked about, it will publish to a Redis topic. So then you have subscribers for those. That's your real-time streaming. And then the last bolt actually makes a post request to the persistence engine. And the value there is that there's kind of a repository abstraction. The message comes in, oh, I've got this type. Let me see what repository I have for you that's responsible for storing, and it will store. You don't need to worry about how it's stored. We'll take care of that for you. We chose Aurora, but this persistence engine is capable of writing to many other data stores. So then the last piece of it is making requests, like you're doing reads and you're wanting to do queries with the data. So we have a read API off of that persistence engine. Any questions?
What's the purpose of logging into S3?
Good question.
Replay.
Replay, exactly. So if something goes wrong, or if they want to, like if for example maybe there's a problem, we got it back in and it got to S3, but somehow it didn't make it to being streamed or to being persisted, we can actually, and I'll get into that in a little bit, we have a utility that will let you rerun that same request through the system.
You can also use that for data mining. So if you wanted to export that data into Redshift or something along those lines, then having it in S3 enables you to do that without having to query big batches of data from Aurora, for instance.
What do you do with rejected events?
Right. So that's the thing that you should see looking at this thing, is there's kind of a hole in the way we went about doing this, and that is that what happens if there's problems here? What happens if there's problems here? Who gets notified, right? And how they deal with that. That wasn't expressed as a requirement for us, so we didn't deal with that case, but it's certainly a hole here. How would you deal with it? Hold on to that thought. We'll get to that in a moment.
It's the question of checking for duplicates.
Right. So in the database, as we're working with an RDBMS, we have these types have primary keys. They're compound primary keys. So the record comes in, we construct a batch insert. Those records attempt to persist a batch. It fails. Then we basically iterate one by one each of those, and basically the database is taking care of uniqueness from the primary key.
So the duplication protection concerns the lower right-hand corner, nothing else.
Yeah, there's no way you can dedupe up here. All you can do is check to see if you've got good data that that you can actually process. Yes.
So when something hits Storm, in essence what Storm is doing is it's running all B1, B2, B3 on each of those records as
Correct.
they come in.
Correct.
Okay.
Each of those messages, and the messages themselves have payload that's processed.
Storm itself is capable of doing more complex types of topologies. That cluster of nodes is called a topology. And so you could do fork join type things where you have operations that you need to do in a certain sequence. Storm was invented by a company called TypeSafe that I think Twitter acquired, and then they were using it for doing hashtag counts, because they needed to be able, if you want to see what's trending, you need to be able to count pretty quickly to know what's trending. So you couldn't do a map reduce. We really were calling it an online map reduce, the instantaneous counting of all of these things. So that was what Storm was intended to do. We're really just using it for a fork feature.
Okay.
The other thing that we were doing too was that inbound requests were compressed. So the request itself was compressed because we had some size constraints on the front door to Kafka. They actually kind of had an SLA that said we won't accept any messages that exceed a certain size of payload. So the largest batch, was it 100, or is it a little bit more of records per type?
I think we cap it at 500, but our customer is only batching at 100.
Okay. Any other questions?
You mentioned the public queue feedback,
Mm-hmm.
but I didn't hear why you need that.
Okay, so Jeff mentioned early on those kind of in the logical architecture. Let's go back to that. So back here, do you remember the difference between Kafka and Redis? The idea that if you're not listening on Redis, well, you're never going to get that message, and there's no way to get back at that message. If you're a client and you want reliable delivery, you can subscribe to Kafka. So basically what we're doing is we're allowing for other clients, other consumers, to work with the data that's coming through the system off of that, off those topics.
In this case, other systems that this customer would build.
Right. I think they had a whole class of applications. What did they call them, Jeff? Listener applications.
Well, I'll mention this too. The private, the format of the message going through the private queue is different because
Right.
it has a wrapper with additional metadata, so that we can identify, which client published the data coming in the front door, and some other pieces of information we can pass all the way through our pipeline. But the customers who want to subscribe to those individual event streams, they don't care about all that metadata. So all they want is the raw events. So one of the reasons why we have it is so that we can package that metadata for our pipeline purposes, but then emit clean messages for the consumers who just want those streams.
Any other questions about the physical architecture? Okay, we'll move on. So now this is kind of getting into the weeds a little bit. You saw in the physical architecture, we had the validation ingestion, we had the facade, the persistence. I'm going to kind of talk through what's going on in each of these in a little more detail. So the ingestion, what happens? They make a post request for a batch of records. It goes through this API. First of all, we have a manifest. Is it known? If it's not known, we don't know. We throw a 404 back. Is the request payload a batch? Then for each event, unpack, and then for each event, we validate. Is it a valid event? If it is, collect it into, the batch of good stuff that we want to post onward. If it's just a single, well, it's the same deal. We basically pass that forward. And we wrap it, as Jeff mentioned, we put these identifiers on it, what client originated the request. We give it a transaction ID so that we can track it. We tell it what type is it, the log event type, so that downstream the bolts know what to do with that message. And if all is good, then we return a 202. If it fails validation, or if everything is invalid, it's a bad request. So are you guys familiar with JSON schema? It's basically the JSON variant of XML schema. You can declare the schema here. So there is a Java library. In fact, it's probably the only one of its kind, but the author has since, I think it was like last year, September, said, hey, I'm no longer maintaining this. But he had basically brought it forward to draft 4 support. And it's still in use widely. It's the only one. Remind me and I will put a link up here at the end for that library. Okay? So here's kind of the persistence workflow. So we have that storm bolt. It makes a post of a batch of log event records. Again, are they known? Do I know how to deal with these things? If or not, it's thrown out. The next thing is, okay, well, if it's a batch, come down here, we do a bulk insert workflow. We identify the repository for that type. Basically, we have a batch of homogeneous log records, right? We construct a bulk insert, basically a prepared statement. So here's where I want to maybe pause a little bit and talk a little bit about MySQL. Who here in the room is familiar with MySQL? Okay, so if I said you want to construct a prepared statement, a batch write request, what does MySQL do by default when you do that? So let's say you have a batch request of 100 records that you want to write to the database.
Probably we disable transactions.
Well, there's that, but there's another thing that's pretty key.
Indexes.
No. So the answer is the default behavior of MySQL is that it will take that batch and for every record it will emit an insert. So it'll do it 100 times. So you'll get linear performance, but 100 times for 100 records. So it happens that there is a flag in the JDBC URL that you can set. It's called a rewrite batch statement, and it's a Boolean. So what it does is it says, okay, I'm going to construct a bulk insert, one insert statement with all of the records in it, and do it once. There's a trade-off there. So let's put that flag aside for the moment and talk about the default behavior. Okay, so let's say you do a batch. It attempts to do those inserts, and what happens is it will throw back, if there's any of those records cause like a constraint key violation or a duplicate key violation or something like that, it'll throw you back an update exception that's indexed, and that index indicates which record within your array of records that you submitted to be inserted are bad. So you can identify right from the exception what those records are. So then what does that mean? Well, if you want to be friendly and resubmit the batch of good records, you can prune those away immediately. Instead of iterating over every record in the batch, you can just prune those bad records and then resubmit the entire batch, and it will save those records. If you have, now let's come back to the rewrite batch flag. If you have that on, you lose that capability. So you get the performance of a single write of those 100 records, but you lose the capability to diagnose what's wrong. So then if there's a failure, you have to loop over all 100 records and resubmit them one by one. So that was a long narrative to kind of what's going on here in the workflow is that you execute your bulk insert. If there are duplicates, you basically have to loop over your records and constructing single inserts. So if they're all duplicates, you're going to get a 409 or conflict. If they're all good, then you get a 204 back because we don't mark each record, like we don't have, what am I looking for here? What's the way of, like when you want to do a 201 created, you can in the header pass a URI back to the record that was created. We don't do that. Yes?
How do you know about duplicates? So is it like a additional unique key, or you do like selects or by
No, basically we attempt to insert. So we're using, if you remember the slide we were talking about Spring and the Spring ecosystem, we use Spring JDBC. So Spring JDBC, we use the JDBC template. We construct a batch input, right? When Spring submits that batch for writing to the database, if anything goes wrong, it will throw back it's like a wrapped exception. They call it a batch update exception. And within that, you can ask it questions like, well, what went wrong? Was it a constraint violation? Was it a duplicate key violation? There's a whole hierarchy of exceptions that could occur on the attempt to write to the database. And you can dispatch that way.
Spring is mapping the JDBC SQL error codes to some kind of like a zoo hierarchy of different exception classes.
That's correct. Any other questions? So other things to note here is that, so we had 30 event types. Well, we have a table for every type. So we've got a plethora of tables in the database, in a single database schema. As I mentioned before, there's an abstraction. So today it's Aurora. All of the records are being written to Aurora, but we could, through this abstraction, say, well, for these types, we want to write, here or there. So it doesn't need to be an RDBMS.
Is there any versioning of events?
I'm sorry?
Do you version events?
We haven't had the need to do that
So
yet.
for clients, they're all super controlled and in sync.
And typically, so this is the
We did
part.
have a meeting today on that subject.
Yeah, and you know what?
But it's
This
the first time in a year and a half. So.
this is the thing that I'm putting the cart before the horse. So I'm giving away something here early on, but when I looked at this, there was kind of an inflection point in the implementation where when we were working with some of our very first consumers, the people who were producing these log events, there was this one guy who in the very first meeting was like, why do I need to talk to you? I've got this data, I just want to persist it. Why haven't you written me an engine that I can just write to without you, without me having to contact you about this stuff? There's a higher level purpose to this, and I think what boils down to the notion of maybe like a consistent data dictionary. Like all of these log events are for properties. They're typically hotel properties. So they have an identifier. Most of them have an identifier like a hotel ID. Well, if we didn't sort of contract with people to kind of look at their data, what they were giving us, and decide how it could be stored so it could be efficiently retrieved, because there's that read part. We'll get into this in a little bit. We didn't build this generic mechanism that they could throw anything at it and we'll take care of all the reading and writing in some generic way. Every type is kind of purpose-built, purposed data structure or table structure with purpose-built indexes that are compound in nature. And, I'll get to it in a moment, the very volume, the large volume of these records necessitated some partitioning scheme with the tables. Who here in the room is familiar with partitions? So what do partitions do for you?
You spread the data across multiple, be it instances or servers of the database.
That's one way to look at it, but for a single table. So why would you want to have a partition on a single table? Or a partitioning scheme on a single table?
You don't have a hot table, you're not putting everything in the same place and
Right.
beating the shit out of it.
Exactly. Well, there's the whole thing of, like the write buffer in the database, is that over time that write buffer gets exhausted and your write performance starts to suffer. So if you start writing to partitions, your buffer, you're protecting your write buffer. On the read side, you're getting the benefit of looking over a subset of the total number of records that you have to do query over. And typically your key participates in the partition. It's actually necessary that the key participates in the partition. Okay, what else can I say? Did I miss anything on this slide, Jeff?
Were you going to talk about truncating by partition?
I'll get to that. Queries. So, GET request, again, the same thing. Do we know how to deal with your request? Did you give us bad parameters? If you gave us everything good, we identify the repository and we process your request with either a select or a sproc. And we return the results. Pretty simple. So these, this type might be, again, the log event, and then what's the key for that log event, the value, and then any other parameters that you might use for filtering purposes. Okay. Lessons learned. I talked about primary keys and the nature of them being compound. With MySQL, key order matters. It doesn't matter in like SQL Server, but it really matters in MySQL. So we had to really carefully deal with each one of those. You'd be tempted to apply secondary indexes to fields that participate in other kinds of queries, but every index that you add to a table slows down write. So we had to get very consciously select that we were only going to have indexes on our primary key. I told you before we're using the MariaDB JDBC driver. It has some additional options that the MySQL driver doesn't have, those being some failover parameters and basically working with and specifying like a read replica or replicas in the connection URL. Right, so this is partitioning again. We opted for every event had a created date. When was it created? So we opted for create date as being the key for the partition. So we're spreading our records across days. And so far that's served us well. I think a typical day's worth of volume, we're talking in excess of 1 billion records written to the database table. Yeah, this is important. Who here in the room has worked with AWS and done deployments? So really, 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 really important for you to co-locate your EC2 or ECS instances in the same region and availability zone as your database. If you don't do that, you're going to incur some serious latency.
Just to clarify, don't put your database on the West Coast and your application on the East Coast.
Yeah, don't do that. Do not do that. Metrics and monitoring. Big, huge in terms of helping you sleuth problems and looking at the performance and health of your application.
So just to be saying, not make sure they're in the same region.
Same region and availability zone.
Availability zone, that would be a bit tricky.
Sometimes it is, but in the case for databases, the RDS is multi-AZ, so you're going to pick one availability zone. It'll typically be your master if you're talking about writes. So you'll have a little bit more latency in terms of your reads and your read replica, because your read replicas typically don't live in the same availability zone as your master.
So is Amazon, is Aurora taking care of all that replication for you?
Yeah.
You don't have to think
Don't have to
about
do about that.
it. How about the partitioning?
Partitioning is your job.
Is your job?
Yeah.
Okay, so you're breaking up your schema
Right.
and figure out which table I'm putting in.
Exactly.
Before you insert. Gotcha.
And that's kind of a one-time setup, right? Like you're provisioning your database to receive a workload. Yes?
Also in the MariaDB driver, you'll specifically tell it, try to connect to this specific instance.
It manages it it knows based on the type of operation where it needs to go and what it needs to do.
And is it smart enough to prefer an instance that's in the same availability zone?
So no, it's not. It doesn't. The way it works is an application makes a connection to the database. That application might live in the same availability zone as the database. If the application is making a read request, the driver is smart enough to know, oh, you want to do this against the read replica. If you're doing a write request, oh, you need to go against the master. That's what it does for you.
So if you have a read replica that's in every availability zone, and you happen to be, let's say, in the availability zone B, the application, the JDBC driver, is it smart enough to access the...
It doesn't know, it picks the most available replica, whatever is the most available.
Are you sure of that?
If you really want to have control, you like hard code all the...
Well, you choose the replica. The replica itself, right, it's like a, with like an ELB, right? You have a host and then you have your instances behind that. Same thing goes for the database. When you provision a database multi-AZ and you select how many replicas you have, basically it's a front. You have the master host and you have the replica host, but the replica host serves as many, 1 to n replicas. So as far as like choosing which replica to read from, I think it has to make, I don't know the explicit details, but I think it has to go off of what's available.
If you're using ELB, you would still bypass the event where you said that you bypass and directly access each instance.
If
Well, with Route 53, you could do like a geo, what do they call that, geo something, where it'll give you the DNS entry for a server that's closer to you geographically. I think it's actually possible. I know that there has been some coordination between the MariaDB developers and the AWS developers, the Aurora guys. So it may do it. I haven't looked at it. It sounds like Chris hasn't. So I don't know that we can say that it definitively does. But I would say that technologically it's possible, and the metadata is there. So it wouldn't surprise me if it exists, but I wouldn't make a statement on that.
So from your perspective, you've got one URL.
Yeah.
Right.
and it's figuring.
The URL is basically the master and the replica, right? So we have a situation where there's one replica and one master. Right. Okay. So we collect stats. So Spring Boot has some integration with Drop Wizard API. It itself has metrics capabilities. But what's good about the metrics, the Drop Wizard metrics, is there's actually other libraries that are kind of third-party libraries. There's one for StatsD. Who here is familiar with StatsD? Okay, do you know what it does?
I just heard about this, like a
You want to take a crack at what it does for the room?
So I never. Go ahead.
Okay. So it's basically kind of an agent, right, that's running on with the application, and it's listening to requests from the application. So metrics, it's collecting those metrics, and at intervals, it's basically publishing those. So you can have StatsD work with Graphite. Graphite will receive those metrics from StatsD on a per instance basis, and then Grafana is kind of like the aggregate. It takes all of those instances and basically allows you to do dashboards that say, well, I want to look at, all of my instances for this deployment in the prod environment, right? And I want to look at this particular metric, graph it over time. I want averages. I want sums. I want to look at multiple metrics and do some aggregation on those. So things like you can monitor CPU, you can monitor memory, you can monitor request rate, you can monitor things like there's a servlet filter that will collect metrics based on the response. So you can look at, well, what are all my bad requests over time? What are my good requests over time? And stuff like that. And then with those things, you can do things like you could publish those out to CloudWatch. And then with CloudWatch, you can set up alerts, right? So as things start to go south, you can be alerted about those. We have Splunk, and Splunk also has, it's basically a log aggregator. So again, there's an agent that's deployed with your application, and it forwards the log records to an indexing engine, and then you can do all kinds of searching and slicing and dicing with their log data. And you can set up alerts as well there. And I think they even have some dashboard capabilities, right? One thing we learned the hard way is that we had a requirement very late breaking, like after we had done most of our work for some audit logging. Like, who originated this thing? What transaction was it a part of, right? And what are the detailed records that were written to the database? And as we mentioned, the volume of records there, we were using logback, and we were using the async appender with logback. If you go look and do a deep dive in the logback documentation, you will find that at high volume, the async appender and even the synchronous appender will drop records. So you're losing log data as data is passing through your system. So we made a very quick change to Log4j 2, and I would highly recommend, if you're looking at that yourselves, to prefer Log4j over logback when you have an audit logging requirement. The other thing is, when you're logging, you want to kind of pay attention not only to the content, but possibly even the formatting, because that's what's going to allow you to, at least if you're working with a log aggregator, maybe it's Splunk, maybe it's an elk stack. Who here is familiar with like Elasticache, Elasticsearch rather, Logstash, and Kibana, right? You want to give some thought to like metadata in your log that's keyed and searchable. And so with these, well, it helps you pinpoint problems. So Right. So there, just thinking back to on one occasion where we had to do some profiling. So we had gotten the Ingestion engine deployed, and we were pumping some traffic through in a stress test. And what we were noticing, watching the VM, was that memory was creeping up and up and up and up. So that was like, oh, we've got a memory leak. What's going on? So we had to start profiling the application, and we learned from profiling that there indeed was a leak, and it had to do with configuration, the way we had configured the validation, the schema validator. And so after some poring over documentation, we reconfigured the validator, and it didn't leak anymore. But it would only show itself to leak under load. Right, so we had to have some way to generate load. Well, we used JMeter for that. And of course, the YourKit was what we used for profiling.
What did you use for test data?
Right, so with JMeter, you can set up templates. And so when you admit your post requests, like for batch requests, we could construct a batch request, and it might have a template to generate dates for a date field in your payload. It might have another template for some string data. So we could pump data through that way. So it's basically auto-generated data.
You're randomly generating. You didn't try to, like, because you have this whole architecture where you're logging all your events, you didn't try to replay them as a load test.
No, I mean, we've done a little bit of that, but for the high load, we were using JMeter generating the data. One of the things that we learned in that, though, is it uses Beam Shell for the templating language. So for the things that you need to generate, so for instance, you don't want to have duplicates, right? So you need to make sure some component of your primary key is changing with each request, so you don't get the duplicates rejected. The problem is if you have too many things in your templates that Beam Shell is having to process, then JMeter can't run it fast enough to generate the kind of load that we
That's
need.
when you switch to Gatling.
Exactly. The problem was that the client's infrastructure was mostly built around JMeter, so we just had to reduce how much randomly generated content we reduced it to just the minimal amount, and the rest is static. So that's a little bit unfortunate. That was the reality of what we had to deal with. We did do some Gatling tests, but we were running those from our own machines, not as part of the deployed infrastructure.
The other thing is, if you've got metrics hooked up, you can look at the results of a run in your metrics. Like you can go straight to Grafana and take a look at a 5-minute window. If it was like a soak test or a capacity test, you might have done a longer run. You can look at how the system behaved during that run. There were reports in JMeter there that kind of showed you what your request rate was and how it ramped up and served the load and met the load that you were asked it to generate. I don't have a ton of experience with Gatling, but I didn't see that capability in terms of reports. They kind of defer to, well, if you've instrumented your application and you're using tools like StatsD, Graphite, and Grafana, go there and take a look at the results of your run.
Gatling uses tons of charts.
It does? Okay, that's good. That's good.
Multiple colors even.
Multiple colors.
I will say that the guy on our team who is responsible for most of that, he far prefers Gatling.
Right. This bit here was, we were looking at, when we made the switch from MySQL to MariaDB, we were seeing some kind of lagging performance with the MySQL client. When we switched to the MariaDB client and we tuned it for use in Aurora, we saw better throughput, write throughput. So, I think somebody had a question about this earlier, about replay capability, maybe. How would we get data back through the system? Initially, we had to build, so we built this platform. And then the client came to us and said, great, you built this thing for us. Guess what? We need your help migrating all this legacy data from our server farm, our SQL Server farm. What do we have to do? We had to extract it. We want to get it into Amazon. So we said, well, if you can extract records from your database and get them into kind of a standard format for processing, we chose JSON records, carriage return JSON records, and we would gzip these files and place them in an S3 bucket and folder in kind of a hierarchy by type, by year, all the way down to the hour. So that gets the data into Amazon, and from there, we wrote a migrator, and it would read from S3. So it was a Spring integration Java DSL application that would read from S3. It would unpack the file. It would process all the lines of that file, transform the content into Java objects, and it would construct a prepared statement and do the bulk insert. It would do it with an insert ignore. The ignore basically says, I don't care if there were any records in this batch that would cause a failure. I'm just going to jam in all the good records. It happened that the data, the origin data, had redundant data. Basically, it had duplicate data in it. And as a requirement of our platform, we don't want to maintain duplicate data. So it was okay to lose that redundant data. So what we would do is we had a kind of a REST interface. We could say, okay, for this type and this date range, go and fetch all of the files out of the S3 bucket folders and run them through and persist them. And then the last step was, well, we got to validate. So what made validation hard was we couldn't necessarily do a record for record. Well, we could, but it would be very expensive, and we didn't have a lot. We were given a very short time frame to do that, and that is actually part of something maybe Jeff can talk a little bit about when we get to the part about. No, you don't want to talk about that. But one of the applications that our client uses is it's like a research tool. He talked about a scenario where somebody maybe they make a booking and they don't get what they want. Well, they have a research tool to compare the supplier data with the consumer data and do like matching. Well, that supplier data is comprised of a number of different log event types, right? And so they aggregate by like joining or bringing all this data together. So the validation was on the aggregate, not the individual log events. So what we did was we wrote kind of an API that would make a call out to their legacy research tool, and that would make a similar call out to our platform, bring the data together, and do basically a JSON unit assertion. Is the JSON equal? What's good about this JSON assert is it's not doing a string comparison. It's actually looking at the data itself and saying, all right, I have records in my array. This record here might be at index position 1. This record here might be at index position 3, but they're physically the same record of this batch. So that's equality. And it does that for all records on each side of the array. So a really nice comparison tool. And you can generate reports that show here were the records that came from the legacy system that are not in the new system. Here are the records that are in the new system that are not in the legacy system. And here's where they match. And so what we did was we ran that through some spot checking. We picked.
So in this case, did you use like unit testing engine inside your production?
So this unit thing, yes, exactly. It would do that. So it's basically a RESTful URL. It was delegating and making 2 REST calls out to each originating system and doing the comparison and rendering the results back to you. Now, you would ask, why didn't we look at anything AWS might have offered there? AWS has a data migration service offering. What made it difficult for us was, I think, one, the shape of the data. The shape of the data in the origin or legacy database farm was different. We didn't choose to model it the same way. We didn't choose the same field names for the data. So that made that very difficult to do. So we basically wound up creating a kind of a custom solution here for data validation, migration and data validation.
Can I speak to that?
Yeah.
So their data migration tool is pretty cool. It'll let you take data from one database and then push it into another database, and you can take for instance from MySQL into Postgres, I think, and it'll even do some schema translation for you. And I think you can do some other transformation stuff as well. And then you can leave it on. So you can migrate your historical data and then leave it running, and it'll continue to process other stuff until you can move your application to repoint to your new database, and then you can shut off the migration service and shut down the old database. So it's pretty neat and an elegant solution that's still in development. You can also use it to pump data into Redshift, which is their data mining query tool. But the degree of difference, I think, for us would have made that untenable. We did find that the majority of the time in doing our data migration was spent in getting all of that data over the wire from the data center into AWS. After we did that, I think it was after, right? AWS announced the Snowball.
Right.
You guys heard of the Snowball? So Snowball is this big case that comes in, and it's got a Kindle, like Paperwhite or whatever on the side of it. That's basically a UPS label, right? But it's actually a Kindle embedded in this plastic box. It's filled with I think solid-state hard drives, and they'll send that out to you for $200 or something like that. And you load whatever you want on it, and then you hit the Kindle, it's a touchscreen. You hit save that you're done, and you call UPS, and then they'll scan the new label that now appears on the side of the thing, right? And then they'll send it to AWS, and they'll load that data into an S3 bucket for you. So that would take maybe a week to go and send it both ways and all that. But it took well over a week for us to send 12 terabytes of data. So we would have saved a lot of time, and it would have been just a few $100s worth. So
But it wasn't available.
Pretty neat idea.
So was your migration incremental too? Presumably you couldn't tell them to stop writing to their database for 1 week.
So yeah, that's a good question. They actually forked. So they're still writing to the old system and they're writing to our new system. And then we simultaneously then migrated all the old data. And now they're continuing to write to both, and we're doing validation across both. And at some point, when they're satisfied, then we'll shut down the old system.
So earlier you mentioned partitioning
Mm-hmm.
and how it provides for write optimization.
Mm-hmm.
But with this migration, did it impact that, given that your partitions were based on write data, read data, that you mentioned?
Right. So let's say you have some log data of, let's call it type A data, and it was today, which is what, the 2nd of June, right? And we're looking at 24 hours worth of today's data, right? All 24 hours of today's data would be in a single partition of a table for this type.
I see, and the migrator took care of it.
The table took care of that. We just provisioned the table, and then as you're doing writes, it's writing to that partition. So
For future migrations, you will have the stuff in that S3 bucket already.
right, and so I think right. Do you remember that slide earlier where it was on the physical architecture where we had that S3 bucket down there, and one of the bolts from Storm was writing back to that facade? So there's a flag on some of the types. Not all of them have it, but some of them say persistent S3. It will take that record and write it to a file in S3. Well, guess what? That's the format that we chose for this migrator. So now this migrator can pull double duty. Not only can it migrate from, an origin system, but it can in the real workflow, replay records through our system.
And of course, in 2 years, they'll move to Azure, so.
Right. Maybe. Okay. I think this is you, Jeff.
Alrighty. So I can speak to that briefly. There were questions raised once or twice from other parties, nobody really directly on our team, about whether we wanted to be, tied to something proprietary or not. And I think it's a fair question. I think that the risk was relatively low in our case. We were willing to tie to something proprietary, but as it turns out, we're still basically MySQL compatible. The only problem that we have is that our data volume doesn't fit in a MySQL instance. So we would have to, shuffle data around, or split things out in a different way. But there really isn't anything that's fundamentally proprietary on what we've done here. We use off-the-shelf open source stuff, and it's just that database that is different. But again, it uses an open source driver and interface. So I want to emphasize, because I'm not sure that it came through. I want to emphasize how important Aurora has been for us. It was a big success. Aurora has been it's said to be 5 times faster than MySQL. We found it to be so. We found it to be very fast, much less expensive, specifically because we don't have to do those provisioned IOPS that Chris mentioned. It's been very performant. It might seem weird to be using a relational database to store non-relational data, because again, this is not connected data. These are just individual log rows. I think that Dynamo, if we used it correctly, could probably do this, but based on the right volume and how it's priced out, I think it would cost quite a lot more, which was on the chart that Chris showed. So, on paper, Dynamo may be a better fit, but when we do the calculations, for the data volume we're looking at, which is we fall below that 60 terabyte limit or 64 terabyte limit, Aurora is an excellent fit for us. So it may not be for every use case, but for ours, we still have plenty of room to grow, and we're hitting our performance targets with room to spare. If we were to build it again today, though, what would we change? One of the things that happened along the way is we felt early on that it was really important to have valid data and not be rejecting it when we got all the way down to the persistence level and try to write stuff in the database, and then the database is rejecting stuff saying, oh, this field's wrong and that field's wrong and these things are duplicates and whatever. We wanted to give people feedback up front because early on, as we were developing it, with our very first tests, people were publishing bad data to us. And so we wanted to give early signal saying, you've published bad data to us. And when we have a queue buffering between our input, our ingestion, and our persistence, there's no way that we can have the database provide that feedback to them, right? Because it's all disconnected. So we needed to do the schema validation at the very beginning to give early signal so that they would know that the data was bad. Then we actually started working with our customers that started publishing data, and they said pretty clearly, the most important thing to us is that you ingest our data, and if we send bad data, then that's bad on us, but we don't care. So they didn't want us to have validation be part of their synchronous call to our HTTP endpoint. So they wanted us to do asynchronous validation. We still insisted on doing validation because we didn't want to send bad data all the way through our pipeline, but we didn't make it part of their HTTP call. And it's turned out that it's worked out okay. We're still paying that cost of doing the validation in the overall processing time on our ingestion server, but they get what they want in having a fast return response from the endpoint. Chris touched on the fact that we don't really have an easy way to identify to someone that there's been a failure later on in the pipeline, or for the people who don't want to know about validation right when they make the HTTP request, they might want to have a report an hour later, or a nightly report that says how many failures they had and of what sort, and we don't really have a good answer for that. So one thing that we could do is have some other new queue pipeline thing that we could send messages to, but then we would have to sort them based on who was the client and what's the contact information for that client, how do we notify them, what are their preferences in notifications and all of that. So there's more that could be done there. We haven't had a lot of demand for that on this side, so probably wouldn't be worth the development cost right now. We've also talked about going serverless. How many folks have heard of the AWS Lambdas? Half. How about API Gateway? Okay, about the same. So Lambda is this AWS technology for writing blobs of code that they will run your code for you. There's a server out there somewhere. You don't ever see it. All you know is that you uploaded this zip, or you write some Node code or Python in a text box, and it just runs it. It scales it up and down, and it's I think a great idea. An API gateway. Oh, that's down here. The server. Well, I guess they're tied together. So the API gateway is a way to have basically a configurable REST endpoint. So if you could use well, actually, Swagger is an open source tool for documenting APIs, and they actually support the Swagger's syntax. So you can create a Swagger configuration, and you can upload it to AWS the API gateway, and they'll create an endpoint that fulfills that contract, and then you can wire it into something behind the scenes, typically a Lambda, to handle the messages that are coming to that API gateway. So you can basically just declare an endpoint as a REST endpoint, publish messages to it, pipe those messages into a Lambda on a server that you don't own or care about, and then the Lambda can handle it, and that Lambda can have direct access to a database if you so choose, or it can publish those messages into a queue if you want to buffer, and then you can have another Lambda listening to the other end of the queue, and then you can have that Lambda be the one that actually does the persistence. So that's where you could use Kinesis potentially. So you do API gateway to Lambda to Kinesis to another Lambda to your database, and you basically have a serverless architecture just like we've built with no servers that you have to manage. You'll still want to do CloudWatch, to get logs. You need to have your monitoring and alerting and everything, but on the whole, the AWS engineers have a good reputation for keeping systems up. So there's a decent chance that they'll do a better job than you will in keeping things working. So that's an alternative that we could consider. Now that does take you down the proprietary route if you're willing to commit to that. It's also potentially the case that you could save money. You have to be careful with the AWS services, how you do your calculations on what your predicted load is going to be. Certain things can be much cheaper if you use their system, and others can be somewhat more expensive. So you want to do some calculations on that when you have some ideas on what your load profile will look like. And so with that, we'll take any questions that you have.
What about Redshift? It was not mentioned in the first slide.
So we listed it as something we evaluated. We evaluated it along the way, not because we wanted it as a data store, so much as that there had been a requirement mentioned as sort of, someday we want to do this, not something that we've had to do, but it really is intended for data mining. It's fairly expensive, I think, depending on how you use it. So I don't know that you would. I think compared to alternatives for data mining, it's probably quite reasonable. But compared to Aurora for simple data storage, it would cost quite a lot more.
It's slow and low. Sometimes.
Yeah. Well, certainly you would not get the like double-digit millisecond response time that we would get. Yeah. Eric?
Have you done any database server version upgrades yet?
Yeah.
I just noticed one annoyance. I haven't used Aurora, but with their Phosphorus version, there is the issue that even if you have 3 replicas, they'll take the whole thing offline for quite a while.
It's not supposed to go down for quite a while. We did have one particular instance where it was down longer than it should have been, and So we made some mistakes in how we did some of our configurations, I think, with our read replicas and how we configured our drivers and everything. I think they made some mistakes because Aurora is still somewhat new, and so there was some stuff that wasn't behaving quite as expected. You can also pick when your windows are for when you do your upgrades so that they have less impact, and I think you can set a different one for your read replica than your write replica, and some things around that, right? But it's supposed to be pretty close to seamless. That was one of the things that motivated our move to the MariaDB driver, by the way, because it has a better understanding of the cluster makeup, because I think it has some specific AWS support built in. But ultimately, we've had data loss several times because of our mistakes and theirs, and that's why it's nice to have that replay capability, because we were able to just go back and then rerun for that time window, and we were able to persist all that data without data loss.
So you've got some schema definitions and validations at the front end, and
Mhm.
also schema
Yeah.
definitions of the table at the back end. Did you couple those, auto-generate one from the other?
We haven't really considered doing that. I haven't really considered doing that. I think it would be a little bit tedious. It's really easy to write the JSON schemas. And we have really simple message formats for the most part, so you'll have usually less than a dozen fields, and most of them are just int strings. We have a few enums or something, and we had some stuff with dates we've had to figure out, but now that we have a couple of samples to work from, it's pretty easy to configure. So there's just not a lot of work there. Usually what our onboarding looks like is somebody says, hey, I've got this new event I'd like you to support, and so we'll work with them to kind of figure out what it is they want to store. We work up the JSON schema, and then we publish that right away, because we want to start seeing them publish data to us, and we want to see them passing the validation, and then we know that we're all on the same page. And it's only after that then we go back in and we say, all right, persistence takes a little bit more work because we got to do some hand coding on some stuff. Because we originally had some JPA to reduce the cost of development, but performance things and all that, we just decided to do hand-rolled JDBC. But because they happen at different times, we've just, and also because the majority of the types are streaming only and they don't need to have the persistence, we've never tried to tie those directly together.
You could, I think, it's like, is it schema first or is it object first? You can create a Java object and emit the schema, or you can create a schema and create the Java objects for persistence. And I think the process Jeff is talking about, that's what we tend to do, is we start with the schema first.
My personal interest, like if we're just storing data that's has been stored elsewhere, like we're not adding new value. For me, the feature of this that excites me is the emitting of the events. So like I'll brighten up more about that because that's the new business value. Otherwise, it's just swapping out one database for another. Really, from their layer, like they don't necessarily see a lot of difference. So I really want to make it super easy to get the new events on board and start getting those events pumped out, and so that new clients can start to come in and consume that data. And then for me, the persistence is the necessary evil that we bring in after the fact.
Yeah, you did show up a GET interface to request data. That presumably is hitting the database.
Right. It's basically invoking a select. Basically, it's invoking a select or a sprock. Right. It doesn't need to. I mean, like I said, that's the beauty of the repository abstraction that it's passing through, is that it could, right now it's RDBMS, but later on it could be whatever you like. It would say if it's a document store, maybe it's like MongoDB.
Does that interface support the kinds of analyses that people would want to do on historical data? I mean, I have no idea what analyses people would want to do. So
typically on the historicals, it's on the aggregate. So they're doing reads not necessarily for a particular log event, but on the aggregate of a number of log events to get like different types of log events. That's what's most valuable to them. So that's where, of course, an RDBMS shines, because you can do those kinds of things, but you can do the same things with SQL data stores and document stores and so on.
All right. Well, if that's it, thank you very much for coming and listening to us. And if you want to just mill around and chat, we'll be hanging around for a little bit here. Thank you very much.
Thank you.